forces in a little more detail. And although this won't be on the quiz, this is extremely important information for the midterm. And what you're going to find is that if you don't have a good understanding of vector addition from Physics 2.8a, then you're going to be a little bit behind the 8 ball here. And so if you are looking at different expressions where I'm drawing force vectors and you're just kind of scratching your head and you don't know how to add those vectors up, you might want to go back and look a little bit at your Physics 2.8a, because really what we're going to be doing in this second part of the semester is looking at the same kind of problems that we did in Physics 2.8a, but we're just going to apply it to electrostatic forces. That means that all those same skills from 2.8a need to still be there, so that you can add vectors, you can take their components, and you don't feel threatened by that or not know how to do it. And so it's really critical then that if somehow you slip through Physics 2.8a without having a good understanding of how to do vector addition and break things up into components and find the different resultant forces, then you're going to be in a kind of a panic situation here. But on the other hand, if you feel good with vector addition, then this should just be another application of something that you already know how to do. And so that's the positive way of looking at it. Usually because this stuff is a little more abstract and somewhat more mathematical, I tell people to increase their study level, put a little more time into this than what you've done so far. In the past I've said double whatever you were doing before, but that might be a little too dramatic because a lot of you I know are already working really hard. But if you're not working very hard, then doubling might be appropriate. Okay, so let's just review where we were at last time. We had this kind of a force relationship for two charges Q1 and Q2. And if they're the same charge, like charges repel, then the magnitude of that force, if this distance is r, is going to be equal to kq over kq1 q2 over r squared. Notice that I'm putting little feet on my q there. The reason for doing that is so that we don't mistake it for a 9. Remember, in our k expression, we have 9 times 10 to the 9 Newton meters squared per coulomb squared. So it's easy to get those 9s mixed up with q's. And so that's just an attempt to distinguish them and make sure that you know that what we're referring to there is charge. So last time we saw that the forces are equal and opposite. We did a calculation where the two charges were equal. We figured out the repulsive force. We did another calculation where the two charges were equal but opposite, and we got the same attractive force. So what I want to do today is go on to a three-body problem. Okay, let's do it on a line still, so we don't have to worry about getting involved with components of vectors. Let's just see if we can do something like this. Let's say that we've got two charges, Q1 and Q2. Let's say they're equal. Let's say it's 10 to the minus 5 coulombs. I like that number just because when you plug in 10 to the minus 5 for Q1 and Q2, and then you have 10 to the 9 there, you get 10 to the minus 1. So you get reasonable numbers in terms of newtons. And that's the only reason why I'm using that number a lot here. It's just to make the numbers come out a little easier so I don't have to use my calculators on. Okay, and so we've got two equal charges. Let's ask, what is the magnitude of a third charge that's placed between these two that will make the net force on all three charges equal to 0. And we're going to specify here that we want that charge to be at the midpoint between the two charges. Okay. So let me just redraw this with Q1 and Q2 being the same value, Q. And we'll put this charge here at the midpoint, the big Q. And so let's say that both of these charges are positive, and we want the net force on all three charges to be 0, with the selection of the appropriate value for big Q. Okay, so and by the way, in these problems, always look for symmetries, because there's a ton of symmetry in this problem. You can see that the force of this charge on that charge is going to be this way. The force, this is going to have to be negative to cancel it out. So I already know it's going to be negative. So if you get a positive value for big Q, then you're not using the basic rule that like charges repel and unlike charges attract. Because that's the only way to get this force and that force to balance out. But also because we have equal and opposite reaction forces, the force of this charge on that charge will be the same. I call that F naught. And I'll call this one F1. And we also know that the attractive force between negative big Q and plus Q is going to be that same value, whatever it is, pointed inward. Okay, and so if we want those forces to be equal, all we have to do is look at one of these charges, because the other one's identical equation. It's redundant. What about the force on the central one? If we want the force on all three to be 0, then this isn't really a condition at all for Q. Because whatever this charge does attracting this way, this charge will attract equally in that direction regardless of what big Q is. So there's no restriction on big Q to make the force on the central charge 0. So we can choose any charge we want. But out here, let's just look at this part of it. And so that's the big key in doing these kinds of problems, is identify which charge you are going to draw forces for. You don't want to confuse yourself by drawing the forces on every single charge. You know, if I do that here, I could draw forces here and forces there. Where am I? You know, I just get dizzy and pass out from confusion. So identify which charge it is that you're looking at. I could have just as easily chosen this one because of the symmetry of the problem. And it would give me the identical equation. So I don't need to write the identical equation twice. Just write it once for that. And so here, let's call this distance here d. If we need d later, that's fine. Let's say that d is equal to 2 meters, just for fun. But let's just leave it as d for the moment. And then this distance here will be d over 2. And this distance here, by symmetry, will be d over 2, whatever d is. So if I want F0 to equal F1, then F0 is the force due to the central charge, is due to the force between these two charges. And so F naught is going to be K times Q1 times Q2, Q squared, divided by d squared. And so that's the repulsive force on big Q. That's this force here due to this charge over here. So this charge then is exerting a force on that one, and this is the distance, and so that's my F naught. But for F1, we're going to want to use this distance, and so F1, this is just the magnitude of it. I'm not worried about the direction. Why? Because I can get the direction just by knowing that like charges repel and unlike charges attract. Okay, so I get my direction of the vector not from the math. I don't go in here and say, well, this is a minus q, this is a plus q, and so I'm going to make this negative. Because then I have to decide what negative means with respect to the coordinate system I've chosen, which is confusing. You're constantly changing your coordinate systems. So just look at the magnitudes here. Kill all minus signs is what that means. Kill all minus signs. And then use the fact that like charges repel, unlike charges attract to get the direction of your vectors. So I can see here, like charges repel, so I know what direction F0 is pointing already. I know that unlike charges attract, and so I know what the direction of F1 is already. So I'm just going to have to set the magnitudes of them equal, and don't worry about those minus signs. You start throwing in those minus signs, you're asking for trouble. You're bound to make a minus sign here. Now, if you're mathematical purists, you might want to do this, but it's like doing, a lot of times it's like 3 or 4 minus sign things that you have to do correctly to get these things right. And so this is a way of simplifying that, which I think is by far the best way to do it. So what we got here then is k little q big Q divided by what? E over 2 squared here. And so what I'm going to do then is set the magnitudes of those equal. And solve for big Q. I may need D, I may not. It looks to me like it may cancel. I may need K, I may not. Looks like it may cancel too. I may need little q, may not. That might cancel, may not. So we'll just see where the math takes us with this. This is k q squared divided by g squared equals k little q big Q divided by d over 2 squared. Okay, so what I'll do here is I'll make this q times q, so I can cancel out one of the q's, cancel out the k's, and so what I've got then is q over d squared equals big Q divided by d over 2 squared. But on the right, you divide by 1 over 2 squared. That's the same as multiplying by 4. So this is 4q over d squared equals q over d squared. So I cancel out the d squareds, and I've got big Q equals little q over 4. Okay, so is that correct? Okay, well, let's say that I do have a number. Let's say the little q is equal to 10 to the minus 5 coulombs. And can I write this as 10 to the minus 5 divided by 4, or 2.5 times 10 to the minus 6 coulombs?
You need a negative sign.
Right, you need the negative sign. Why don't we have a negative sign here? Well, because we killed all of the negative signs to begin with. So don't forget to put it back in at the end. It doesn't make sense if it were positive. And it couldn't possibly work if this were a positive q, because then that would be pushing both F1 and F0 would be pointing in the same direction. So they could never cancel. So don't forget the negative when you're all done. So, like so many of these problems, the math isn't that bad. But what is a little tricky here is conceptualizing the problem and seeing which force is due to which charge, and then canceling out the common factors. So this is minus Q over 4. Any questions about that? All right, and you can follow that along here. I did that in here, but go to the next one. Okay, now this next problem is one of your group quiz problems for today. You've got a charge minus 2Q and a charge plus Q, and we want to know where along this axis to place a third charge, big Q, so that the net force on big Q is 0. Okay, so that's something I've given you some things to think about here, and you might want to refer to this later when we get back to that problem. But I'm going to move on to this problem, which I've actually worked out. So in this problem, we have a dipole. Okay, so why do we make such a big deal about dipoles? Well, because any polar molecule has a positive and a negative end. And that's what gives rise to molecular forces. So to bring molecules together to form a crystal, or whatever kind of covalent solid you want to make, you need to look at electric forces from dipoles. So dipole just means that there's no net charge in this whole thing. But if you look at the whole thing as having a charge separation, that could be, for example, represented by the water molecule. So we've got one oxygen and two hydrogens. The oxygen has many more protons in its nucleus than the hydrogens do. And so that means that the oxygen can pull harder on the hydrogen's electrons than the hydrogen can. And so that means the electrons spend more of their time over near the oxygen. And on the hydrogen side, the electrons have been ripped off. Not completely, they're not gone, but they spend less time over here and more time over there because of the larger amount of attractive force due to more protons in the nucleus attracting more negative electrons. Okay, so it's this attractive force, a positive negative, that allows for water droplets to bead up. Okay, that's why you have a water droplet. If I pour a little bit of water on this table, it'll bead up. And that's because of surface tension. That surface tension comes from the fact that the positives and negatives bind themselves together. It actually takes a little bit of energy to pull them apart. Okay. And so that's just one example of a dipole. There are many, countless others. But that's a really common one. So given that there's a lot of applications for this, let's take a look at the force of a charged particle along the axis of a dipole. And this is similar to the first problem that I gave you on the group quiz. Although in this problem that I gave you on the group quiz, the two charges are both positive. Okay, and so what you can do then is take the work that I've done here and just change it up a little bit so that the forces both point away like that rather than pointing away and toward, which is the case in this problem. Okay, so you'll have a similar kind of an expression, but it won't be quite the same when you do this group quiz exercise. And by the way, this will be due along with chapter 35 and 36 homework. Before the quiz. outline for you on the home page all of the things that are going to be on the quiz. But basically, it'll be everything, double lenses on, that I've covered in class. And all of those lectures now are posted except for the one on Tuesday. And then that one and this one will be posted pretty soon. Maybe later today or tomorrow. Okay, so here, what we want to do then is find the force on this third charge as a function of distance. And just for convenience, let's take the separation distance between the positive and negative charges to be 2L. And in this problem, let me see. I'm using, okay, I didn't specify what Q is. So I'll just leave it in terms of Q for the moment. So that I'll stay consistent with the notes. If I want to plug in numbers later, I'll do it. All right, so this distance then is some variable distance x. And we want to find the force on big Q as a function of x. Okay, so in this problem, this is the first time that we're getting into components. Remember that you did a lot of components, Physics 208A. You had to break things up into x and y parts, then add them together. I used to assume that everybody knew how to do that. And then I found out that a lot of people had just completely forgotten it or never really learned and somehow squeaked through 208A without that information. But you need it again here. So this distance is the actual distance between plus Q and plus little q and big Q. And so this distance then is the square root of x squared plus L squared by the Pythagorean theorem. This distance here is L because the total distance is 2L. So I just define the total distance as 2L for convenience to make the map have less numerical constants in it. And so I know what direction that's going to be because I remember that like charges repel. So if I call this charge 1, then I can call this force here F1, and that angle there I can call theta. But here's the key thing. I may not know what this angle is, but I do know that vertical angles are equal. So that means that this angle is equal to that one, and I can get this angle from this reference triangle, which involves the distances. So did everybody hear that? I can get this angle, because it's the same as that one, from this reference triangle that is in terms of given quantities, like the distance. So that's really super important that you see that that's what it is that we're doing. And then over here, we'll have, if I call this charge 2, then this force is going to be attractive. Call this F2. But notice, I'm not drawing any of the forces between these two charges, because I just want to know what the force is on big Q. So that's the key thing that clues me into the fact that I'm just drawing a vector diagram here. It doesn't make it wrong to draw the vectors here. It just makes it more confusing. It's going to take you a lot more time. It's not going to get you anywhere. So we're just looking at the forces on that charge. And we can see that there's some symmetry here. Always look for symmetries. Why? Are the symmetries always there? No. Usually the symmetries aren't there. But I'm going to give you problems where there are these kind of symmetries to simplify the problem so that you don't have so much math to do. So you always want to look for the symmetries. And so one symmetry that we have here is that this distance from charge 2 to big Q is the same as the distance from charge 1 to Q. So this distance here is also the square root of x squared plus L squared. So we have the same distances. And so what can we say about the magnitudes of F1 and F2? They're the same, right? Same distance, same magnitude of the charges. Remember that the force goes like K little q big Q over R squared. So little q and big Q have the same magnitude. The distance is the same. So they must have the same length. So that's the symmetry in this problem. The symmetry is that because the distances and the charges are the same, the magnitudes of the forces are the same. So the magnitudes are equal. So I could just call it some generic F. And I'll call that F then. Well, that's just K times little q times big Q divided by the square root x squared plus L squared squared. But that just gets rid of the square root. So that gives me K little q big Q divided by x squared plus L squared. So that's the length of F1 and F2. That doesn't tell us that they're pointed in the same direction, because they're not. But it does tell us that the lengths of those vectors are the same, and so that's going to help us with vector decomposition. So let's do that next. Remember, with vector decomposition, what you want to look for are the components that add and also the components that cancel. Okay, so which part of this, if I call this my xy coordinate system, I'm going to define y as positive down, just because both forces are pointed down. What can I say about the x and the y components?
The x components cancel.
Good. The x components cancel. So we've got an F, got a theta there, and we can say that this component is F cosine theta. This component is F cosine theta. But the F's are the same and the angles are the same, so that means that they cancel. X components cancel. By symmetry. It's okay if you just say that. You don't have to necessarily draw the whole thing out. But then notice here, this part you do need to draw out. The surviving components are F sine theta. And so the F sine theta components add. Okay, and so the sum then of these two forces, because the x forces are gone, is just going to be the two y components. So when I do this as a vector sum, I say the sum of the forces is going to be equal to F1 vector plus F2 vector. But in reality, because the F cosine theta components cancel, what we're left with then is just 2F sine theta times j hat. Where j hat is our unit vector that points in the y direction. Now if you define the y direction to be up, that's okay, but then that would need to be a negative F. Okay, so the next thing to do then is to substitute in, because we've got everything in terms of theta and F, but instead we want to write F and theta in terms of given quantities. So assume that the given quantities are little q, big Q, L, and well, we're doing it as a function of x, but we're going to write it in terms of x. even though it's a function of x, we want to write f and theta in terms of those given quantities. And of course, our Coulomb constant k. Okay, so we've got this expression then for f. That goes into there. What about sine theta? No clue from this triangle what the sine of theta is. Well, we can go to this similar triangle here, and we can say that the sine of theta is equal to the opposite L divided by the hypotenuse, which is the square root of x squared plus L squared. So that sine theta goes in here. And then once we've done all of that, then we can just simplify, and we're done. Any questions so far? The rest is just a little bit of algebra. So does anybody have any questions on how I'm setting this up? Why I'm doing it the way I am? If you're given a certain length, let's say, a certain values for these charges, then we want the force in terms of those quantities, not in terms of f and theta. So that means we have to write those quantities that have to do with f and theta in terms of our given quantities. And we get the reference triangle here gives us the angular dependence on those quantities. So when we plug in, we get the sum of the forces. And remember, this is a vector sum, head to tail addition type of thing. If I were to add these two together like that, then this would be the resultant. That should be F total, which would be in the down direction or the positive y direction. So that's what I'm doing here. When I solve, I add up the x components, they're 0. Add up the y components, it's equivalent to just our regular head-to-tail addition, which gives us the original, the same thing. But this is more mathematical and gives us a better approach to the problem. This is 2k little q big Q divided by x squared plus L squared times sine theta L divided by square root x squared plus L squared. So we're getting really close now, but we're not quite there. We need to simplify this a little bit. So we can write this then as F total equals 2k little q big Q L divided by, and then this is x squared plus L squared to the 1 times x squared plus L squared to the 1/2. So when we put them together, what does that give us in the denominator? Good. X squared plus L squared to the 3/2 powers. And so it's the square root of this cubed. That's what the 3/2 power means, or to the 1.5 power times some unit vector that points in the j-hat direction. Okay, so we can plug in numbers for those if we want to. Let's ask how much smaller is the force at x equals L as it is at x equals 0. Let's draw the vectors for x equals 0. That puts them right in between. That. So here's little q, here's plus q, here's minus q. So we're going to have a repulse. We're looking at this charge. This is when x equals 0. And then this is at some other value for x. We could set it equal to L eventually. But let's just do it at x equals 0 when it's right in between. And then let's see if it simplifies to that when we set x equal to 0. Okay. Well, what we've got then on big Q, we've got a force due to the top charge, that's F1. And we've got a force due to the bottom charge that's pointed in the same direction, that's F2. So they're both pointed in the same direction because positive repels positive and positive attracts negative. So they're both adding together, and the magnitude of F equals F1 equals F2, because we still have that symmetry that we talked about over here. K, little q, big Q over some distance squared. In this case, that distance is what? L, good. This is L. This is L. So it's the same L. So both of them are the same. It's going to be K, little q, big Q over L squared. And so that'll be times some unit vector in the j hat direction. We define the j hat direction to be down. Okay. And so then let's see if that reduces to this expression when we add them together. So F total would equal 2k little q big Q over L squared. Does everybody see that? That's going to be our F total when we add up the F1s and the F2s. We just get twice what it is for one of them because of the symmetry of the problem. Now let's go back to this and see what happens if we evaluate this at 0. F of 0. That doesn't mean F times 0. It means F evaluated as a function of x at x equals 0. So that's going to be 2k little q big Q L divided by 0 squared plus L squared to the 3/2 power. So what's that? L squared to the 3/2 power. L to the third. So this is going to be 2k little q big Q L over L cubed, or 2k little q big Q over L squared. I'd be very concerned if it weren't the same. It means that I would have made a mistake, okay? But I did. So those two agree, and so we see then that this expression does reduce to this one in the limit as x goes to 0. Any questions about that?
How do you add force 1 and force 2 together again? Because
They're a head-to-tail addition vector sum. So that's what I was talking about before. You need to know how to add vectors. So you go from the tail of the first to the head of the second.
why do they add? Because the charges, because the top is
The
positive.
direction of the forces is the same. It's the forces that add. The charges aren't added. It's the force of this charge on this charge added to the force of this charge on that charge. And so those are both vectors and add together.
Gotcha.
It's like if I push on somebody, then somebody else goes, hey, I'm going to push with you. I'm going to help you. You know, maybe you're pushing your refrigerator or something. Twice the force, because you're pushing twice as hard. Any other questions? Okay, now let's evaluate when x equals L. Let's find what the force is there. Now, can you see that when x equals some other value other than 0, it's not going to be at its maximum anymore? Because you're wasting some of the force components. And then we showed last time that when you go to infinity, out here, way out there, those forces exactly cancel, completely cancel, when you're out really far. But when you're in close, they're partially canceling, But when you're at 0, they don't cancel at all. Okay, so at infinity, they completely cancel. At 0, they don't cancel at all. Anywhere else, intermediate, some cancellation, but not total. So let's just see how much cancellation we get. At x equals L. So then we have f of L, right? So this is f of x in general. This is the way I'm writing it. The force as a function of x, but now I'm evaluating at x equals L. So that's going to be 2k little q big Q L divided by L squared plus L squared to the 3/2 power. So that's going to be 2k little q big Q L divided by 2L squared to the 3/2 power. Okay. And so what we're left then with is just do it over here. This is going to be 2k little q big Q L divided by 2 to the 3/2 power times L cubed. And so that'll be 2k little q big Q over L squared times 2 to the 3/2 power. So that's the difference between them. How much smaller is it? It's going to be f of L divided by f of 0 is going to look like 1 over 2 to the 3/2 power. Because everything else will cancel. Over here we have f of 0. Here we have f of L. We see everything's the same except for that 2 to the 3/2 power in the denominator. So that's how much less it is. Everything else cancels. Did I go through that too fast? Yeah.
F of L, does it not have the ratio F of L over F of L equals 1 over 2?
F of 0. This is f of 0. So this is just this without that factor of 2 to the 3/2 power. So this is smaller by that factor.
What did it put? Ratio?
2 to the 3/2 power is more than 1, and I know that this ratio is less than 1 because this is the maximum value. Okay? You can go through the math. Go ahead and do that. Just plug in f of L, f of 0, cancel everything else, and that's what you'll be left with. Any other questions? Okay, so I did that on the page that I passed out to you. You can double check that and see whether that makes sense in terms of what you have written down in your notes or what I wrote up on the board. 2 to the 3/2 power is square root of 8. 2 cubed is 8, square root. Okay, sometimes, a lot of times when I was at the university, they wanted to know whether you could be a tutor or not, and so they'd say, what is 8 to the 2/3 power? Okay? And so you'd have to think, well, the cube root of 8, or is that the one I wanted? 2 times 2 squared is 8, yeah. The cube root of 8 then is 2, and then that squared is 4. So if you say 4, then they give you the job. next, what I'd like to do